Okay, any questions before we start about electrostatics? You should be having many questions. Any one of them you would like to ask? Okay. Now this week we will be starting magnetostatics. Well, you will see that mainly we will be repeating what we did in electrostatics with the magnetic fields and currents. So there will be many parallels between electrostatics and magnetostatics. And one thing to pay attention to, we are still doing statics, but this doesn't mean that there is no motion. The charges will be moving. Charges are in motion. But, for example, all the time derivatives, we will define what the current density is, etc. Any time derivative is zero. So that is what we will be meaning by statics. So we will have charges that are in motion. Now the magnetic fields, if you think about the first, well, people used magnetic fields much before Maxwell. We had the magnets, we have the, how do you call them? Compasses. That they basically align with toward the north of the Earth. So if you have a compass, we know that it should, all the compasses basically, they point in the same direction. It's not an electrostatic force, there are no charges on the compass, so you can just bring a test charge and see if there are any electric forces. There are no electrostatic forces, so we define some kind of a different kind of force. So, and the direction of this new type of field, just like in analog to electric field, we will define a magnetic field, and the magnetic field direction will be in the direction of this compass. Now, there are no single charges, so these compasses basically have two poles. They just behave like a dipole. So you can assume that they will create a magnetic. These compasses create their own magnetic field, which you can model by the magnetic field created by the electric field, let's say. So it will be some proportionality constant. We don't know what yet. And let's call the magnetic dipole moment, just like the electric dipole moment, as m. So the force will be 3m minus m dot r hat over r squared. And if you take one of the compass just orients itself, it rotates. Since it rotates, it means there has to be some kind of a torque acting on it. So if you remember what the torque acting on a dipole, electric dipole was, if you place it in an electric field, just like that, the torque acting on a magnetic dipole will be this magnetic dipole moment cross product with the magnetic field times some constant k. Let's just assume it's the same constant k. Well, in fact, let's just keep them different, k and k prime. They can be different constants. So this will be the torque. Now, of course, if we are talking about the magnetic dipole moment and the magnetic field, we should be able to measure them. Without measuring them, it won't make any sense to talk about them. The direction is it's the direction of the compass. So you just put a compass in a region. If it points in a given direction, then the magnetic field is in that direction. So that is kind of easy. But what about the magnitudes of the magnetic field and the magnetic dipole moment? Now, to determine that, we will be, okay, so we will try to determine the product. We will try to find a physically observable quantity which is proportional to their product, and another physically observable quantity which is proportional to their ratio. So that will be our strategy. First, let's try to find if there are some physical quantities that we can measure that will be proportional to these quantities. Now, let's start with the torque. Well, if you take a compass, it has the north and the south poles of this compass. And you put it in a uniform magnetic field, let's say in this direction. the magnetic dipole moment, let's say, we will define it in the direction of from south to north. And let's assume that it makes an angle theta with the magnetic field. So what will be the direction of the torque? It will be into the screen. Let's say that is the z-axis. So the torque acting on this dipole will be just K mb sine theta or cosine theta. Sine theta in the z direction. Whereas the angular momentum in the z direction, let's say, is, let's call I this moment of inertia times alpha. What is alpha? Angular acceleration. Well, minus theta double dot. Because of the weird way I define the angle. So there's a minus sign. So you see it's rotating like this with that definition of theta. So if theta is increasing, the velocity is in the negative direction. So that's why basically we have that minus sign. And we know that the Lz should be equal to d by d. The time of change of Lz should be equal to the z component of the torque. And so we have no, this is I alpha, sorry, I omega. Angular momentum is I omega. So minus I theta double dot is equal to K mb times sine theta. For small theta, this is approximately K mb times theta. Or theta double dot should be equal to minus K mb over I theta. So it's basically, it will be oscillating back and forth with period of oscillation squared is K over I times mb. So if you can if you measure omega squared, its oscillation frequency, and the moment of inertia of the compass, we will know. And just look at it, measure its density, etc. So that's something known. K is, well, not exactly known for the time being, but let's keep it like that. For the time being, assuming we know K, m times b is equal to I over K times omega squared. So K will be some constant. I is just some constant depending on the shape of the compass. Omega is something we measure. So once we measure omega, we determine the product of the magnetic dipole moment and the magnetic field. So that is how we can measure the product. No. Omega is not theta dot. But theta is theta 0 cosine omega t plus delta. So you see, this is my compass. Let's say the magnetic field is in this direction. My compass will do such a motion.
How do you write the equation?
Which one? This one.
Minus I theta double dot equals K and sin theta.
This is equal to this one. This is equal to this one.
Can you repeat where we got the minus sign from?
Minus sign, you see, as theta increases. Okay, so as theta increases, what is the direction of the angular velocity? Yeah, this direction. This is minus z. So if you like, L is equal to I theta dot, but in the minus z direction.
So it's all dependent on our reference.
Yeah, I mean, you see, I could have chosen the z direction to be in this direction. Then I wouldn't have minus in the definition of Lz, but I would have a minus sign in the definition of the torque. Nevertheless, this equation over here would have a relative minus sign between the left and the right hand sides. So that minus sign is not convention dependent. But where that minus sign comes from, whether it comes from the z component of the angular momentum or the definition of the torque, is another issue. So if this is the z direction, positive theta is this one, positive increase of theta. Negative theta is in this direction. That is my negative theta.
You don't know what K is, right? It's just a proportionality constant.
For the time being, it's just a proportionality constant. You see, if you look back at these equations, let's say I can write this as K prime over alpha M cross alpha B. And then this equation would just be K over alpha, alpha times B is equal to alpha times K, 3M minus M dot R hat over R squared. Now what this tells me is, I can just, instead of calling some quantity B, I can call alpha B as my B. It will just correspond to a change in K and K prime. Change of units. I can in fact change my units K and K prime as I wish. It will just change how I define my B. So that is something we will use eventually.
And this equation would be, is it just by analogy to the dipole moment?
Yes. Now later on we will derive it, that it actually works. But for the time being, it's just an analogy. Just imagine yourself. You don't know about the magnetic fields yet. But you know this effect of the compass. So there's a force acting on the compass. And the compass just behaves a lot like a dipole, electric dipole in an electric field. If you take an electric dipole, put it in an electric field, and it will just oscillate around the direction of the electric field. It just behaves similarly. The first simplest guess would be just assume a similar form for the magnetic field of a dipole. And the torque acting on this magnetic dipole. Eventually, you should of course do more and more experiments to test whether your description is consistent. But first, let's just describe it like this. Of course, to be able to describe it in this form, we should be able to measure M and B. If we cannot measure M and B, it's just useless. So that is what we are trying to do. We have this postulate for the magnetic field created by a magnetic dipole, and also the torque acting on a compass created by a magnetic dipole. So for the time being, this is just a postulate. The first thing we have to show on the way to show that these make sense is first to determine how we can determine these M and B. Of course, we have to determine two things, their magnitude and their direction. M is in the direction of the compass, so this direction we already know. And the direction of B would be the direction in which the compass aligns. So that's basically the torque equation. So we are saying that we have this compass. There's something that just forces this to align in a given direction. So we just call it, it creates this torque, and we call it B, whatever creates this torque. Then there's also this compass creates a magnetic field on its own. So we just postulate that it is just like an electric dipole. Of course, the next experiment I would have done will be take a magnet, take a dipole. We know how the electric field lines of the electric dipole are. Take a dipole, magnetic dipole, a compass, a strong compass, fix it, take another compass, and determine what are the directions of the magnetic field lines. So it should be, well, that is probably something they have done. So if you take a north and south, if you put let's say a compass over here, it should align in this direction. If you put the compass over here, it should align in this direction. And so that if you just draw these magnetic field lines, they should look like this. So this is kind of an easy experiment to do. Just take a magnet, which is also a compass, take a second compass, a sensitive one, fix the magnet, just move the other compass around. So you will be able to determine the shapes of the magnetic field lines. And this just looks like the magnetic electric field lines of our electric dipole. Well, it's not exactly the same, but if you are sufficiently far away, they look quite similar. The shapes. If the shapes are similar, then their directions are similar and their magnitudes are similar. The dependence of the magnetic field on the position should be also similar, because the shapes of these field lines determine how the field changes from point to point. So this observation, you can say that it's not exactly a postulate, but rather a experimental observation. Your observation is this: you take a magnet, fix it, move a compass nearby, and then you can determine the shapes of the field lines, which are identical to the field lines of an electric dipole.
When we talked about the intensity of the field, we compared them and we said that the dependence of the intensity on the distance are the same.
Yes.
So, which means that we have already considered that they are the divergence of the magnetic field is zero when we are away from any magnet.
Yes. Well, again, it's a measurement though. It's not an assumption. Because we know that since the field lines are the same, we already know that in an electric dipole, the divergence of the electric field is zero away from the dipole. Well, the divergence of the magnetic field, since the magnetic field is similar to the electric field, it should also be the same away from the dipole. So inside the dipole, we don't know yet. We will drive it. So now we know how to measure the product of the magnetic dipole and the magnetic field. Now let's take this dipole, put it in, fix it. This is our M. We fix it in space. You see, here we had our unknown magnetic field that we are trying to measure, and the magnetic dipole moment of this magnet that we are trying to measure. So the same magnetic field, we already know its direction. Let's say it's in this direction. How do we know it? Well, we put a compass there. We put our magnetic dipole in the magnetic field, let it oscillate, eventually it will settle. And then once it settles, we know the direction of the magnetic field. By measuring this oscillation frequency, we measure the product of the magnetic dipole moment and the magnetic induction. The proper name of this B field is magnetic induction. So we know the product of their product. And so now I take this magnetic dipole and position it perpendicular to the to this B field. And then I take another compass, put it over here. And it will settle in some other direction. Let's say this angle is theta. This is M prime. This is some other magnetic dipole moment. Now at this place, this M prime just settles in the total B field, total magnetic induction, which has a component in this direction which is given by B, but it will also have a component in the perpendicular direction due to this M. Well, why do I know it's in that direction? Let's look at this expression over here. Well, we have assumed this distance is, let's say, R0. So this is R0, this is B0, or Bm. But R0 hat is nothing but M hat. R0 hat, remember, is a vector in the direction of, a unit vector in the direction of R0. But M is in the direction of R0, so M hat is the same thing as R0 hat. So this is equal to K times 3M minus M R0 M times M hat divided by R squared, R0 squared. So this is 2M K over R0 squared. Where M is nothing but M in the M hat direction. And this angle over here, let's call it theta. Tangent theta is nothing but 2K over R0 squared M divided by B. Or M over B, this will be equal to R0 squared divided by 2K tangent theta. So by just measuring that angle theta, we already know this distance R0. We can just measure it. Assuming we know what K is, then we can determine M over B. Let's go back. We already know M times B. Well, one of them should be K prime. Torque is K prime. So this is K prime. Now, let's go back to this any questions on this one? You see, I have a region where I have this magnetic field that I'm trying to determine, to kind of measure. I have this magnetic dipole, compass or a magnet, and I also want to measure the magnetic dipole moment of this compass or magnet. So I do two experiments. One of them, I put this magnet in the region of the magnetic dipole moment, let it rotate freely, add some friction so that it will the oscillations will damp eventually. So it will just settle in the direction of the magnetic field. So I know the direction of the magnetic field. Then let's say it is settled like this, the magnetic dipole. Now the magnetic field, let's say, is in the upward direction. It's settled like this. Then you just kick it slightly. It will oscillate around this magnetic field direction. I measure the frequency. And that frequency allows me to determine what is the product of the magnetic field and this magnetic dipole moment, magnetic induction and the dipole moment. I can determine its their product. This is my first experiment. Then I do my second experiment. In the second experiment, I already know that the magnetic field is in this direction. I take my dipole, fix it vertical to the magnetic field. Then, of course, the magnetic field, let's say at this point, magnetic induction at this point will be just a superposition of this already existing magnetic induction plus the magnetic induction created by this dipole. There will be some resultant vector. The direction of the resultant vector will be determined by these two quantities. To determine this direction, I take another dipole and put it right over here. This new dipole will align itself with the new direction of this, with the direction of the total magnetic induction. So I can measure that direction, I can measure this angle, so I can determine the direction of this magnetic induction. Well, the total magnetic induction over here is just the superposition of these two magnetic inductions. One that was already present, the other one that is from the magnetic dipole. So if I determine this angle of this right triangle, just take the tangent, and that allows me to determine the ratio of the magnetic dipole moment to magnetic induction. So if I have these two, and if you just multiply them, m squared is just r0 squared I over 2k k prime tangent theta. And if you just divide them side by side, b squared, yes, omega squared. And b squared is I omega squared divided by r0 squared tangent theta times twice k over k prime. Now, the only thing left is how do we determine this k and k prime? How do we define them? So, since we are defining these quantities, and k and k prime, let's say, at the moment we do not really know, we can have some choices. What would you like to have the magnetic field? Which unit should it have? Because we can, by just choosing this parameter alpha and redefining b by alpha b, I can change the unit of b. If alpha is something that has a unit, then I can always redefine the unit of b. What would be your choice of the unit of b?
The easiest is to make us magnetic. And we know that we need to do. I said the easiest is to make us the constant unitless.
So you want b unitless?
B, no.
Well, a good choice. The choice that was made was the unit of b is equal to unit of e. What is the unit of E? Let's see, what is the energy density? Do you remember? 8 pi E squared. Right? What's the unit of energy density? joules per meter cube. So the unit of E squared is joules per meter cube. Okay. What is the unit of this I omega squared divided by R0 squared tangent theta? What is the unit of I? Kilogram meter squared. What is the unit of omega? 1 over second squared. What is the unit of R squared? Meter squared. So this is kilograms meters per second squared divided by meter squared. Well, kilogram meters per second squared is joules per meter squared. Did I forget some factors over here? No. So let's see. M times B, is it correct? I theta double dot, this is L dot, is equal to the torque. Torque is K prime MB sine theta. So K prime over I MB, omega squared is K prime over I MB. MB is equal to I omega squared over K. B is mk over R0 cubed. Remember, the dipole is not squared, it's the cube. You see, the potential of the dipole goes as 1 over R squared. So the force goes as 1 over R. The field goes as 1 over R cubed. So here we have R0 cubed, R0 cubed, R0 cubed, meter cubed. So the coefficient, the unit of B squared is the unit of E squared multiplied by the unit of K over K prime. Well, the easiest choice. The unit of K can be equal to the unit of K prime, whatever that unit is. That would have been a nice choice. Now, furthermore, you see, I had this freedom of redefinition since I'm defining it for the time being. Where is it? Okay, I can choose the unit of alpha such that K and K prime have the same unit. Furthermore, I can choose a numerical value of alpha such that K and K prime are equal. Not just have the same unit. They will be equal. I can make that choice. They will be equal to each other. Because if they are not equal, I can just change my definition of the induction field and make them equal. Now, let's go back. So these are my expressions. Okay, the unit of B now these are equal. Unit of B is joules per meter cube instead of B squared. What should be the unit of M? You see, let's first look at the unit of B from the first equation. Well, the unit of B is the unit of K times the unit of M divided by M cubed. The unit of which should be equal to joules per M cube, or the unit of K times unit of the M, the magnetic dipole moment, should be equal to joules. No, sorry, I have this squared. Unit of K squared times unit of M squared should be equal to joule squared meter cube. So this is one relation I have. I take the square of both sides.
No. Unit of B
B squared is
squared.
equal to okay, it should be joule. Not joule square.
You take the photo.
Oh, okay.
We took a bit correct last.
This is joule. Yes. Now, okay. K squared M. Now let's look at the torque equation. What's the unit of torque?
Meter.
Which is joule. At the same time, it is equal to the unit of K, unit of M, times the unit of B, which is joules per meter cube. Does this give a different equation? So let's just take the square of both sides, joule meter cube, K times M, K squared M squared. They're both consistent with each other. From this step on, we will need some more measurements to determine what K is. But again, by just choosing the value of K, you are basically setting the scale for the magnetic field or the magnetic dipole moment. It will turn out that K is 1 over C, eventually.
Why did you choose it with dimension? Why did we choose it with dimension?
It looks nice. Well, we could have chosen it to be dimensionless. Well, you see, I choose it to be dimensionless in my research because I said C equal to 1. I even choose C to be dimensionless. Let's say for historical reasons. Well, it's not 1 over C. By the way, that C over here is not the speed of light yet. It's just some number. We will see eventually that it is the speed of light. And that observation will just lead to all this revolution of the special theory of relativity. Because once you say that C is the speed of light, people start asking with respect to which reference frame. We are not specifying any reference frames over here. These laws that we are writing, it should be valid in any reference frame where you have this magnetostatics. But then we will study magnetodynamics, so where the charges are free to move, accelerate, the time derivatives need not be 0, but still, even in that case, the C appears to be the speed of light. So the question is with respect to which reference frame? at least up to the special theory of relativity, we thought that the speed or the velocity is always relative to our reference frame. So if you say the speed of light, then the question automatically is with respect to which reference frame. And there was all this idea of the ether, this hypothetical thing that fills the universe. So these equations were valid in the reference frame in which the ether was at rest. So people try to find a consistent description of nature using this concept of ether, but practically it didn't work. So one thing about all the courses that you are taking, in the courses, we are always telling you things in a particular order where in that order the lecturer usually doesn't fail. So whatever assumption they make, it always works. Well, that is not how in reality it works. So you make assumptions, there are hundreds of people making hundreds of different assumptions, and 99.99% of all of them except one fails. So in a sense, doing research is, the norm in doing research is failing. Not in succeeding to get an answer, but you're just failing, finding an answer. So let's give a break, and then we will continue.